Hi, it's Mr. Mac, and we're going to be looking at some more advanced problems in circular motion.
This is Mr. Mac. He can explain things really well and is a lot of fun to watch. You can subscribe to Mr. Mac's physics channel. You will find mathematics problems, science demonstrations, astronomy and space pics, physics calculations and simple explanations of advanced concepts.
So what are we learning to do? We're learning to describe and analyze qualitatively and quantitatively circular motion, as we did in the previous video. Success criteria. We will be able to solve complex questions for objects executing uniform circular motion in a variety of situations. And so in this video, we're going to look at a little bit more complex questions. Here's worked example 8. It's a circular motion problem. In these problems, we're going to use a WISE strategy. What's happening? So we draw a diagram, write down the data that we know. We want to isolate the unknown. So we find an equation, write it down, we might have to rearrange it in order to do the next step, which is substitute. So we substitute the values, making sure that they're all in SI units. And lastly, evaluate. Is it a realistic answer? Have we got not only magnitude, but the units? If it's a vector, do we have the direction? And have we rounded to the correct number of significant figures? So here's the question. An ant has somehow managed to find its way onto a record sitting on a turntable. When the record turns, it rotates at 45 RPM, or revolutions per minute, in a clockwise direction. The diameter of the record is 18 centimeters, and the ant is positioned 4 centimeters from the record's center. The question is, and there are several parts to it, convert the record's angular speed from RPM to radians per second, which of course is SI. Find the ant's angular displacement after 2 seconds in radians. How many revolutions has the ant made on the record after those 2 seconds? And determine the tangential velocity of the ant. And if the ant walks to the edge of the record, which is 9 centimeters from the center spindle, will the magnitudes of its tangential and angular velocities increase, decrease, or stay the same? As you can see, this is quite a complex set of questions. So what's the first step? As always, data and diagram. So we find out what's happening. So you can see there, drawn a circle, got the radius of 4 centimeters where the ant is on the record, and its tangential velocity vt. And just showing the direction is clockwise. So the first question, or the first part, A, is to convert the record's angular speed from revolutions per minute to radians per second. So here's the data. The angular speed is 45 RPM and 1 revolution is 2 pi radians. And here's a formula that will calculate the angular speed. We simply take the 45, times it by 2 pi, and divide by 60 because there are 60 seconds in 1 minute, to give us an angular speed of 3 pi on 2 radians per second. Happy to leave it like that and move on to part B. Find the ant's angular displacement after 2 seconds in radians. The formula is omega, that's the small omega, standing for angular velocity, is equal to delta theta on t, that's the change in angle over time. And substituting for omega, which we had in the previous question, as 3 pi on 2 equals delta theta over 2 seconds, which, rearranging delta theta, the change in angular displacement is 3 pi radians. Part C asks how many revolutions has the ant made on the record after 2 seconds. So we simply convert the 3 pi into number of revolutions, and we do that by dividing by 2 pi, which is why in part A it's easy to leave it as 3 pi on 2. So when we find that, we do the calculation, 3 on 2, 1.5 revolutions after 2 seconds. Part D, determine the tangential velocity of the ant. Again, the data we have r is 4 centimeters or 0.04 meters, converting to SI units, and the angular speed is 45 RPM. The period, in other words, the time it takes to do one revolution, is 60 divided by 45, which is 1.3 seconds, correct to two significant figures. The formula we use, V equals 2 pi r on t, capital T standing for the period. In some textbooks that's written as capital P, but T reminds us that it's in SI units of seconds. Substituting 2 pi times 0.04 divided by that 1.3 repeater that we had in the first part there, we find that the calculation ends up as 0.19 meters per second, correct to two significant figures. And of course the direction is at right angles to the radius at that point. Part E, the ant walks to the edge of the record. Now this is quite a hard question because we're dealing with changes, and we want to know what changes if the ant walks from roughly the middle to the outer edge. So firstly, in moving to the edge, the radius of the circle that the ant moves has increased. So the ant moves a greater distance in the 1.3 seconds for that one revolution. So that means that the ant's tangential velocity has increased. The new position of the ant does not change its angular velocity since the record is solid and every point on the record moves through the same angle. Of course, that's at 45 RPM. By the way, you probably noticed that the animation in the top left is not going at 45 RPM, but 33 1/3 RPM, and it's a long playing record, or an LP. The ant's angular velocity in that whole process has stayed the same. Here's a question from a past HSC, and presented the students with simply a circle with two labelled dots and an arrow showing direction, and that's to represent a horizontal disk that rotates at a constant rate as shown in the diagram. 2 points on the disk, X and Y, are labelled, and the question says that X is twice as far away from the centre of the disk as Y, and the students are required to compare the angular and instantaneous velocities of X with those of Y. Now before we dig into this, firstly, what type of question? I'll just put it up the top there. The question is a compare question, and I've underlined the key verb in the question at the top. That means we have to do some writing. We possibly may have to do some calculation to back up what we're saying. Now look at the diagram and ask what's missing from the diagram. What's some information that we're given that we can put on the diagram? So I encourage students to write all over their question paper. And here's what's missing: a diameter, a radius, another radius, and the centre of the circle. So I've labelled there RY as the radius to the point Y, and RX, the radius to the point X. Well, here are some similarities. If we're comparing, we want to see what two things are the same in both. So both X and Y are undergoing circular motion, let's state the obvious, in an anti-clockwise direction, using the diagram as information. What else do we know? Both X and Y have the same angular velocity, and they're synchronized, both at the same angle relative to a position on the stationary part. Well, what are some differences when we're comparing? Don't just stop with similarities, although in our common vernacular we have a difference between comparing and contrasting. In an HSC question, we want to make sure that we compare similarities and contrast the differences. The instantaneous velocity of X is faster than the instantaneous velocity of Y because, of course, it's farther out from the centre. And Rx, the radius, is twice the radius of y, as shown in the diagram, given in the question. So that means the instantaneous velocity of x is given by v equals r omega. So Vx equals Rx omega, which equals 2 Ry omega. That means that Vx is twice the instantaneous velocity of y. Now that's an important distinction. And 3 marks are given for correctly comparing angular and instantaneous velocities of x and y. Here's a more complicated example, again taken from a past HSC. And it's worked example 10. And in this we're going to be describing and deriving circular motion. Again, there's a stimulus diagram, and here it has a protractor, what looks like a protractor. It's labelled, there's a car roof, there's a light string, there's a mass, and the view looking towards the front of the car is labelled. It's a 4-mark question, and it says the apparatus is shown attached horizontally to the roof inside a stationary car. The plane of the protractor is perpendicular to the sides of the car. The car was then driven at a constant speed v on a horizontal surface, causing the string to swing to the right and remain at a constant angle theta, measured with respect to the vertical. Here's the question. Describe, and I've underlined the key verb, how the apparatus can be used to determine features of the car's motion. In your answer, derive, and there's another key verb, an expression that relates a feature of the car's motion to the angle theta. Now this is a hard question, and it's designed to sort out those who can simply describe to those who can describe and derive an expression. It is question 35, so we expect as the paper goes on that the questions get harder. So what do we do with this? Where do we start? Well, the first step is diagram and data. Okay, so on the diagram there are some missing labels. So we want to label W for weight. We want to label left and right because we're looking towards the front of the car. We want to label the tension in the string as T. What else do we want to do? Well, the apparatus, we start writing down what we know and describe. The apparatus can measure the acceleration of the car horizontally in a left to right direction. It is an accelerometer. If there are no horizontal forces acting on the car, the pendulum remains stationary with its string vertical, and the forces of weight, W, and tension in the string, T, are balanced, equal in magnitude, and opposite in direction. There is no net vertical force and no net horizontal force. As the car is driven, the string swings to the right at a constant angle theta from the vertical. This indicates that a horizontal force is acting on the car to the left, causing the car to undergo uniform circular motion. Now, before I go on, have a look at all the words I've underlined. They're all adjectives. And when you describe something, when you're writing down a description, the more adjectives you add in, the more you have described it. A described question has sometimes been said as writing down the features of whatever you're looking at. But I think it's easier if we actually understand that we're adding in adjectives so that we're not just naming things. Have we answered the question? Well, not quite. Let's put in some axes and let positive axis be up in the y-axis and to the right in the x-axis. And I've drawn the diagram again. This time it's a free body diagram with vectors shown. T for tension, W for weight as before. You can now see it's at an angle, and there's a net force relative to the interior of the car, apparently to the positive x direction, or the right, and we're interested in that force. So when the pendulum swings to the right, the forces acting on the mass are weight, tension, and net force. Vertically, W, the weight, equals negative T cos theta. Use trigonometry. Cos, remember, is adjacent over hypotenuse. So W is mg, but remember G is in the negative direction. So mg equals T cos theta. Rearranging, we find an expression for the tension force T is equal to mg on cos theta. Horizontally, F net equals ma. From the perspective, or the sitting inside the car as the car is moving. That is negative T sine theta, remember sine is opposite over hypotenuse, equals ma. It's in the opposite direction. So we substitute for T that we just found. So negative mg on cos theta sine theta equals ma. Of course, sine over cos is tan, and we can cancel out the masses. So we're left with an expression that says negative g tan theta equals a, the acceleration. The car has centripetal force equal to and in the opposite direction to the force acting on the mass. From the frame of reference of the interior of the car, of course, appears like there's a force going to the right, but the car itself is undergoing circular motion, and so there is a net centripetal force in the direction to the left. Therefore, we can equate that with the acceleration in centripetal motion. So G tan theta equals v squared on r, or rearranging, r equals v squared on g tan theta, and we can calculate the car's radius of turn just by looking at v and g and theta. Now that's a hard question, but 4 marks for an answer that relates observations to features of the car's motion and derives an expression that relates the radius in terms of theta. Well, here's some comments from the markers. In better responses, students were able to recognise that the car was moving with uniform circular motion and to use vector analysis to derive a relevant relationship. Areas students to improve include reading all the material in the question to ensure that the correct scenario is being analysed and showing all the steps in the derivation of an equation. Students need to engage with the image and to understand the situation. The car was turning, not accelerating down the road, so read the diagram carefully. Comment from the markers in 2019 was most students got this wrong. So direction does not overly matter in this case, but it is important that students derive an expression, as this is a requirement of the syllabus. A lot of students gave a formula but didn't actually derive it. Well, I hope that's helped you understand what's required for HSC and complex questions. So now that we've seen projectile motion and circular motion, in the next video we'll be looking at motion in a gravitational field. I'm Mr. Mack. Thanks for watching.